Right, good morning everybody. Hopefully you can all hear me okay. And hopefully you've also all got your goodie bags. I know we're on for a fairly full-on day, so there's a few bits in there to keep you going. And please feel free to rustle away while I'm presenting, I don't mind. So obviously the little slot I've got in here is all about considering design and risk internally. And I want to tie that a little bit back to quality. I think just looking out the window here, well, one, it's a spectacular view. I was blown away when I came in this morning. But it also reminds me just how much construction is going on in London. It is, I think, a market that is very sensitive to quality, but equally quality is something that should be enjoyed across all sectors, across the whole country. So in terms of what actually makes a quality home, well, there's quite a few positive things that we tend to think about. Gwyn alluded to a few of them earlier in the home quality mark. And it's things that you can include in a sales specification, not to belittle them, but plush furniture, surround sound speakers, the quality of the finish, all these things that people are willing to pay extra for, very positive things that we can put into a home. The areas that we get involved with, it's very difficult to market a home based on quality that reduces risk of condensation, that might improve daylight levels. Ultimately, there are a lot of things that if they aren't done properly, you can pretty much guarantee that your homeowner, if they move in and they've got a condensation risk or they've got overheating, they will be knocking on your door and telling you. So these are things that we need to be doing right, effectively the basics as an industry, to ensure that homeowners are getting quality in their homes. So what I'm going to do today is just talk through 4 different items that you can include to ensure that the design of a home is actually going to achieve a decent quality when we're talking about indoor environmental standards. And those things are air permeability, obviously air tightness, a drafty home, not particularly one that we want to live in. Also going to take you through thermal bridging or heat loss from cold bridging junctions. 2 issues there. One is obviously a heat loss and the other one is potentially a condensation risk. And then also internal daylight. A room such as this, lots of natural daylight, it makes us all feel good. It's also very marketable. And then last but not least, something that, forgive the pun, is probably going to be a hot topic moving forward, but summer overheating. It is something that we as an industry are still learning about and something that is already causing issues, let alone taking into account rising temperatures from climate change. So I think one of the keys here as well is each one of these is a topic in its own right that I could talk about and other people could talk about for days on end. I don't want to do that because I've only got 20 minutes, but each one of these is also interlinked. We can't look at just thermal bridging without having a look at air permeability. Internal daylight factors have a huge impact on summer overheating. So whilst there are issues in their own right, we do have to take a pretty holistic approach to addressing them. So if we start off with thermal bridging, it is a topic that's become more relevant in the industry over the last few years. In terms of what you have to do under the approved documents, the building regulations, well, this is the extract, and it effectively says that you need to iron out any reasonably avoidable thermal bridges in a development or in a home. Now, that can be a little bit woolly, and there's a whole lot of stuff behind that around what you as a developer or an architect might have to do. In terms of what we have to assess as assessors, we have a list of junctions. This isn't all of them. Hopefully this just gives you a bit of feel for the detail that we need to be moving towards as an industry. But these are some of the junctions that are available to us when we're doing an energy assessment to review how much heat loss you've got from any of your cold bridges, from your junctions. We need to review all of these junctions, and then we need to apply what we call a psi value to those junctions. So that's effectively how much heat do you have from any junction in a house. And a psi value can come from a few different places. So at the moment, in terms of the regulations or the documents that are available to us, we have a few handbooks. Now, these are industry-created handbooks in a lot of instances where you can build to a certain detail or design to a certain detail, and this handbook will tell you that will achieve X level of performance. The first one we've got up there is the accredited construction details. That's owned by DCLG, and available on the planning portal. That's been around for a while now, probably in need of updating, and I know there are some other schemes that are coming up in the future with the potential to replace this. We've then also got some details that give slightly better performance on that. You've got the enhanced construction details from the Energy Savings Trust. The constructive details, that's an industry-driven set of details from what was the Aircrete Products Association. And then we've also got some Concrete Block Association details. Now, these, and there are others, this isn't an exhaustive list, Now, these details are available for any developer. They're all up there for you to use, but they are specific to certain construction types. Now, a lot of the work that you'll see just looking out the window here, concrete frame, steel framing systems, there are no standard details available for those at the moment. So the final option that we'd probably have to look at is doing bespoke modelling. So what we would do is actually model the heat loss of a particular junction. We can then use that figure in the SAP calculation if we want to, and I'll come on to that a little bit later on this afternoon when I run you through the SAP software. And that assessment gives a more accurate feel for what the heat loss from a junction is going to be. Now, this is all quite theoretical at the moment. We are very much, as an industry, looking at heat loss from thermal bridges at design stage. There is very little as-built coordination, as-built rigor to ensure that what is designed in these junctions is actually implemented on site. So thermal bridging is a heat loss issue, first and foremost, under approved document L. It is also potentially a condensation risk issue. This is something that really does tie back to quality. If you've got condensation appearing in your development, and that could potentially lead to mold growth, like I said earlier, you can be fairly sure that people are going to be hammering on your door and saying, why have I got this? So yes, we have a box to tick in terms of heat loss, but it is also a box to tick in terms of condensation risk. And the guidance is set out in approved document C, and to be honest, that is not particularly helpful. You've got two options. The first one says build to the accredited construction details, but as we know, these aren't applicable to all developments, and especially if you're working on something that's more bespoke. You will probably have to follow this guidance, which is in BRE document that sets out the modelling that we have to do and the standards that you need to achieve in order to reduce condensation risk. Again, this is very much theoretical. There are some design considerations that we have to work around, but ultimately, and we have to look at things called temperature factors, but ultimately, the guidance roughly says that if you've got a home heated to 20 degrees, the external temperature is -5, you need to ensure that the internal surface, where you've got a junction, is going to be higher than 14 degrees to avoid condensation. Again, that's a very theoretical assumption. This is something we're doing as a desktop exercise, and it's always a good idea to build in a bit of a buffer. You want to make sure that if you are looking at a junction for condensation risk, that the performance in your software, you want to make sure there is a buffer in there so that if we get to site and what's actually designed isn't completely implemented as per the drawings, that risk of condensation isn't going to occur. So that's what we'd have to do in terms of actually modelling it. Just a quick example of probably how not to do it. This was a junction we got asked to model, and what we have here is a concrete balcony bolted onto a concrete frame structure. We didn't even need to model this to say effectively you are going to have a risk, well, one, of excessive heat loss, and also condensation risk. So what we've got in the junction is heat loss running straight out from the concrete frame, out through the balcony. If you wanted to design this more appropriately, you're probably looking at firstly maybe insulated balcony connector. You could insulate the balcony externally and wrap all the way around, or you could insulate internally. Now that may not give you the appropriate result that you need, but I think some of this is coming back to the basics. We were asked to model this junction. There was an assumption this junction could be acceptable under the current regulations. It's not. So there is a bit of an education piece that we need to be doing as well to make sure people have the tools and the awareness to design out thermal bridges and also design out condensation risk. But it does need to be a bespoke approach. It's not a one-size-fits-all. It may well be for some of the larger developers doing standard house types. They might be able to adopt the details I talked about earlier, and they might also be able to create their own details. But ultimately, we do need to be looking at this on a project-by-project basis, certainly within London, and certainly where you're looking at bespoke construction types. So that's thermal bridging. Moving on to air permeability, something like the approved accredited construction details gives guidance on air permeability and thermal bridging. So the two can be interlinked in places. Firstly, what do you actually need to do under approved document L? Well, if you're building a new dwelling or a non-domestic building of 500 square metres or more, you need to ensure that you achieve an air leakage rate of 10 metres cubed per metre squared per hour. So it's effectively what's the volume of air seeping out of the building envelope per hour. It's uncontrolled ventilation. It's not something we necessarily want. I think it's important to say as well, this figure of 10, and the gentleman was talking about passive house earlier. Passive house requiring a standard of 0.6. It's air changes per hour, so it's a slightly different measure. But obviously, passive house is substantially better than the targets we're setting in the UK. But I think it is worth mentioning that in order to comply with both L1A and L2A, you will need to be testing at much lower figures. So it might not be quite as bad as it seems from that headline. There are obviously some other benefits to air tightness. It's not just a regulation that you need to tick the box with. Can reduce occupant discomfort. If you're sitting next to a window and you've got a draft coming through, that's something the homeowner is going to notice, and there's going to be a perception around quality with that. It can also cause damage to the building fabric. If you've got air moving in and out of a property through the fabric, you've got potential for moisture penetration. That's going to cause damage over a longer period of time. And I touched on it a little bit, but it can be quite a cost-effective route to Part L compliance. If you have experience of building airtight homes, if you can do that, then chances are you may have opportunities to comply in a more cost-effective manner than if you're achieving tightness figures of maybe 7, which, to be honest, we probably shouldn't be looking at this day and age. In terms of designing into air tightness, there are two elements here. Obviously, we need to design and then we need to implement, and the two can get lost sometimes. But I think the really important thing is just understand exactly what we're trying to achieve. If you are designing to an air tightness of 7 meters cubed per meter squared per hour, that's going to be a very different strategy and a very different conversation with the design team than if you're trying to design to 0.6, the passive house standard. First thing first, you need to identify your airtight barrier. So what are we going to actually use to ensure that this building is airtight? Is it going to be wet plaster, parge coat, double plasterboard, or are we going to have to look at air tightness taping so that we're actually really getting our air tightness performance to a very low level? There can be some issues with the actual design, so the layout of the building. So if you've got rooms in roof, if you've got the ceiling, the sloping ceiling running straight into skirting boards on the upstands, that can be very difficult to seal. So certain design proposals could actually have a knock-on effect in terms of actual as-built performance for air tightness. You might have some structural issues. You might have structure that compromises the air tightness barrier, joist hangers, or are you going to go for inbuilt floors? A lot of these things need to be considered, and this is why we need a bit of a joined-up approach. We've got to make sure that anyone who is doing works that could impact the air tightness barrier is aware of their influence ultimately. And I've touched previously, but there is industry guidance out there that can be used, things like the accredited construction details. It's a checklist to run through to ensure that you are achieving a reasonable level of air tightness. That will not get you to the passive house standard. That is certainly an over and above and something that needs real design consideration. So if we designed our property to achieve a certain level of air tightness, it's then down to implementing it on site. Now, there are lots of things that we can do to ensure that we're going to achieve what we set out to achieve. I'm just going to touch on, I think, what are some key principles. The first one is having responsibility. I think it's really important to have one person who is ultimately responsible for the air tightness of a dwelling. That person can oversee the trades, and they can make sure that if there are any issues, they get rectified straight away. I think the next thing is accountability. Every trade needs to be accountable for their impact on the air tightness barrier. Whether that's the plumber, whether that's the electrician, they will all be doing works that could interfere with the strategy. So they need to be aware of what they're doing, and they need to have responsibility and accountability to put right any defects they may cause in the air tightness barrier. Training, it goes without saying, I think. With anything like this, we need awareness across all the site operatives so that everyone knows what they're doing and what the impact they could have on air tightness. A lot of this comes down to attention to detail. We need to build in time to the program to make sure that ceiling's being done appropriately. We're not just talking about skirting boards, it's loft hatches, it's all of our electrical sockets, our building services. Someone needs to be taking the time to check that this has all been done. And that probably leads me on to the second point, which is have to allow time for air testing on site. There are many, many occasions where we get called out to test a site and someone has CML the same day. So if we're testing and for whatever reason they can't achieve the figure they need to, that's a real issue if they've got handover in, 2 hours' time. So we need to be building in more time in the program to make sure that we're testing that property and achieving the standards that are required. just a quick nod to Part F. It's not something that we get specifically involved with, but Part F sets background ventilation rates that you need in a property. The background ventilation rate that you need if your air permeability figure goes below 5 increases dramatically, and that can be very difficult to achieve with certain types of ventilation, namely System 1, so extract fans, trickle vents. So I think it's very important to, when we're assessing your targeted air permeability, to be very honest about it. If we're putting in a figure of 7 in the calculation, that implies that you might not need the more stringent or the increased background ventilation rates. But ultimately, if you have a track record of achieving 4.5, 3s, you need to be putting in an appropriate ventilation strategy. Otherwise, you're going to run the risk of things like condensation build-up in the property, especially in rooms and roof. It's an area that we see quite a lot. So, I guess that was all a little bit of theory. Just a few examples of how not to do it. I hope these all come out clearly. But anyone take a stab at what we might be looking at in this photo? No? Well, just very simply, we've got, well, one, there's no skirting board in this one, but also there's no ceiling between the floor and the dwarf wall that you've got in the room with the roof. So that's an area where you're going to get air leakage straight out into the loft space. The next one, hopefully that one's a little bit more obvious. That is, well, there would be a toilet going in there a little bit later down the line, but ultimately this was when we were called out to do the air test. So there's a bit of education there in terms of when is a property actually ready for air tightness testing. Gaping holes there where you're going to get a huge amount of air leakage. Again, skirting board, not sealed, down at the bottom. These things are small details that can make a difference. It's not going to get you down to the passive house standard, but it's certainly things that we need to be doing from a best practice point of view. And then lastly, this was a non-domestic build, and we've obviously got preformed concrete there, big gaping holes. Those should all be sealed. So a lot of this is around education. A lot of it's around just making sure that there is the attention to detail and making sure that someone has the responsibility to deliver these items. So that's air permeability. The next one I'm just going to touch on is internal daylight. And when we're talking about internal daylight in domestic buildings, we're talking about what's called an average daylight factor. It's effectively what is the ratio of natural daylight within a building to outside the building. Obviously, the higher the figure, the more daylight you have in the room. In terms of regulatory standards, there aren't really that many. We have BRE's guidance note, which is quite a long document. I won't go into it in too much detail. And that document effectively says you need to be, or guidance is you would achieve the figures we got listed there, 1.5% for all of our habitable rooms except bedrooms, which have a slightly lower target. We don't spend as much time in our bedroom, and when we do spend it, it's usually at night. So the importance of daylight there isn't quite as great. That guidance note is often applied by local planning authorities, and they will look for homes to be meeting those standards. But the actual guidance note does say it is not the be-all and end-all. So there is a bit of flexibility there. The Code for Sustainable Homes, God rest its soul, did set a slightly more stringent standard for our kitchens. And then last but not least, we've got the home quality mark, which Wim was talking about earlier. That is setting more stringent standards, 2%. Average daylight factor, obviously affected by how much glazing you've got. Transmittance, so how much light comes through the glazing. You can get glazing systems where we have potentially a lower G value, so solar gain, but still allow light to come through. Design and form of a room, if it's a very deep room, it's probably going to be a bit darker at the back. And then also external obstructions. Right now, in this room, we have very few external obstructions, but if you've got a ground floor flat, chances are you are going to have some obstructions. You're not going to get anywhere near as much daylight in there. And that's why daylighting, ultimately, is difficult to regulate or put an absolute standard on that everyone has to meet, because there will be site constraints. What does that actually mean, all of that? Average daylight factor, 1.5%. Well, if you've just got a flat, 20 metres squared, your kitchen, living room, you need a glazing ratio of about 20%. If you want to go up to the 2% target for the home quality mark, that increases to about 26%. Now, this is very much a best case scenario, really. So if we started throwing in obstructions, additional shading maybe from balcony to minimise your overheating risk, then that's something that we need to factor in. So a bit of a bespoke approach on this one. Obviously, the benefits, well, enjoyable quality of life. We all like lots of high levels of daylight, but it can also have an impact on energy efficiency as well. More daylight you have, the less energy consumption you're going to have from your lighting systems. So that's internal daylight, and on to the last topic, which I think is one that's going to be discussed very, very heavily over the coming years, and that is summer overheating. The issue, well, there are many issues around it, but firstly, it's a very subjective measure. I think if you're like me and you've ever had an argument over the thermostat, people have different perceptions of what is comfortable, so it can be quite hard to define. But we do have some guidance out there. CIBSE Environmental Design, Guide A, says that living areas shouldn't exceed 28 degrees for 1% of annual occupied hours in a year. Standard for bedrooms, slightly lower, so we're looking at 26 degrees. Reason being, people tend to be more susceptible or more aware of a higher internal temperature when you're going to sleep. So that's the general issue that we have. In terms of design considerations, there are many, and there is no one-size-fits-all approach to reducing a risk of summer overheating. Firstly, you'd have to have a look at site context. Is the area you're in, is that going to absorb heat? Albedo is what we call a measure of how much heat or light a surface will reflect. So if you're building a home in the middle of a field, or you're building the home next to a car park is going to be absorbing much more heat. The potential risk of overheating just from site context is much, much higher. Building form and orientation, things like floor-to-ceiling heights. Has the building got the ability to regulate the internal temperature? Possibly the biggest one, solar gain. Obviously, the amount of glazing you have in a building. How are you going to limit solar gain? Is it going to be shading? Is it going to be G value, which regulates the amount of solar radiation that comes through? Thermal mass, ability of a building to absorb energy. So if you've got a building with a very high thermal mass, it can regulate excess buildup of temperature. What we would say with a high thermal mass is that potentially once it achieves a certain temperature, it can be a bit harder to cool down. So you tend to find you need to really ensure that that building isn't going to heat up. Internal gains, big issue. If you've got things like community heating pipes for a district heating network, if they're not appropriately insulated, and have come across instances where that doesn't happen, you've got a huge heat buildup that can happen in communal areas. And then, well, last but not least, the occupant. Can you control the behaviour of the occupant? The answer is, in most cases, no, you can't. If you design a ventilation strategy that relies on openable windows, and that person doesn't want to open their windows, then all of your hard work at the design stage has just gone out the window. So that's a big issue, and I think that comes back to education of the occupant. So the modelling tools that are out there, the first one is SAP Appendix P. This is, I guess, the definitive regulatory standard. It's an output of the SAP calculation, and to be honest, it's fairly basic. And it's important to say it's a compliance tool. It is not a design tool. So we're taking inputs, and that tells us whether we are compliant with the regulations or not. It takes into account where you are in the country, how much solar gain you get, what's the external temperature, it does look at thermal mass, although not in a huge amount of detail, and also the ventilation rate you're going to get through a property to purge any heat buildup. It doesn't really look at the context of the site, so it doesn't look at a heat island effect, which you might get in London or another big city. It doesn't look at occupant behaviour, and it doesn't take a room-by-room approach. It only looks at the entire build. A more detailed assessment, which I won't go into too much detail because I know we've got a slot on it this afternoon, is what we call dynamic simulation modelling, which does go into that kind of detail, starts looking at a room-by-room basis, and we have much more flexibility on the inputs, so we can change a lot of the inputs to try and accurately model that dwelling. I think the big issue is that because there is so much more detail in it, we need to ensure that there's rigor around that data input. We can't just be making assumptions without communicating it. It's very important to be feeding that back to the design team. Last but not least, summer overheating. What's the reality of it at the moment? We have buildings that say they are compliant with SAP Appendix P that are overheating, and it's been an issue for a while now. It's not just an issue with the increased standards from Part L 2013 or even Part L 2010. So there's plenty of studies out there. I won't go through them all now, but they do suggest that homes we're building at the moment are overheating. Some types of home are more susceptible to others, single facade flats. Overheating can be a year-round issue, not just a summer issue. Now that's probably setting off quite a few alarm bells. And homes we are building at the moment to meet future standards, although they are potentially not happening now, zero carbon, are also going to have issues with overheating. So it is something I think the industry needs to one, understand a lot more effectively, and two, ensure that we are using the appropriate techniques at the right time to model our overheating risk. So, just to finish up, to summarise, as I said, don't rely on SAP Appendix P to guarantee that your home won't overheat. It's not a robust enough tool. We need to be looking at dynamic simulation modelling, which is at the moment also a requirement of the London Plan. Air permeability, don't assume anything. We need to make sure that you're using best practice on site, you've got accountability to make sure you achieve the targets you need. And then last but not least, thermal bridging. It's one of my favourite topics, but we really do need to be assessing our heat loss from these junctions. We're building a lot of junctions at the moment where we're assuming they are performing well, and in reality, they might not be. So it is a focus area. And that is me. So thank you very much for your time.